And we did the tutorial. So, and you have been introduced to this approach of using solving with constant specific heat and also variation specific heat. Right, so and isotopic relationship, so which is nothing new to you. I mean, Otto diesel cycle. Okay, and if you look at the textbook, I mean, there is this chapter on the Ericsson and Stirling cycle. So we skip that. I mean, that's you can look at on your own. Ericsson and Stirling cycle is on your own. So we skip that, and today we look into the gas turbine cycle. Okay, so before we start, please sign up your attendance, right, on the Power Apps, those of you who haven't done so. Okay, so first thing first will be announcement. So yeah, that lab that we should start it this week, but we have problem, and because most of our staff has gone for this vaccination, booster vaccination. So yeah, and they after they get vaccinated, I mean, mostly they will get 2 days off. So we are lacking the number of staff to handle the lab, and we have to postpone the lab to next week. And also the lab has not finalized the schedule yet, but we will finalize the schedule, yeah, within this week. Okay, so I will put up the schedule on Ulearn. So I'll yeah, we will look at your preference. I mean your choice number 1 and choice number 2. Look at it, right? And we'll make the grouping based on that session. So and quiz 1 will be okay. So quiz 1 will be next week. Will be multiple choice. We have not decided on which day yet, but yeah, probably a Friday, or yeah, I will discuss with the class rep. I mean the exact time. I mean there will be a special session, just probably a half an hour. So you'll be online, right? So quiz will be online. Quiz. And also assignment number 1, it will be posted online on Ulearn. Right, assignment number 1. So you have to do it individually. So quiz 1 will be up until we learn today, right? So which is all about chapter 9. Okay, so any questions so far? Yes. Okay, so yeah, I think it will be for 4 people per group. Maybe some of you will get 3 people per group, but maybe 4 people per group. Yeah, all we go at the same time. Yeah. So yeah, we'll try to make it maintain the SOP as possible. So we make it like 4 person per group. Okay, and there will be 3 labs experiment. I mean, this semester. Okay. All right. So yeah. So that's all announcement. So lab quiz 1 and assignment 1. Okay, so today we'll look into gas power cycle, still on gas power cycle, but on the gas turbine cycle. Okay, so for today's we look into specifically the Brayton cycle. So we're still the idle cycle, like we were introduced in Oro cycle and diesel cycle. So where you know that it's a hypothetical cycle where irreversibility are not considered. I mean, the losses, friction are not considered, and it's like the most idealized cycle. Um, yeah, the same goes with Brayton cycle. So Brayton cycle, but Brayton cycle is meant for gas turbine. Right, so these are the lesson outcomes for today. Right, so now we go into introduction for Brayton cycle. So this is a schematic diagram of the real gas turbine cycle. And you have been introduced to this steam turbine cycle, right, in your thermodynamics 1. Remember, steam that is being condensed and then being expanded in a closed loop, right? In a closed loop for steam cycle. But for gas turbine cycle, the real physical one is an open cycle. Like what is shown here, you have a fresh air going to compressor, and the compressor increase the pressure, right? Okay, the pressure, and then goes into the combustion chamber. And where combustion chamber, you got a fuel combust, so energy goes into your working fluid. Right, so from fresh air, it will combust. So it's a mixture of the air and fuel combust. So you have the flue gas, right? Flue gas means the product from the combustion, it goes into the turbine. And as you know, you have this high energy fluid that goes into turbine. So and the turbine is expand, and then with that you produce the work net output, and then it will goes up to the exhaust gas. So this is the real processes for a gas turbine, right? So it's an open loop. Fresh air goes in, goes compressor, goes into combustion chamber, mixed with fuel, combust, chemical process, heat goes in, and then goes to the turbine, it's expand, produce power, and the exhaust gas will go off to, So it's all not mixed. But in an idealized cycle, which is the Brayton cycle, we want to make it a closed loop, right? So in Brayton cycle, it tends to make a closed loop so that, in thermodynamic cycle, you want to make it, it goes off to the process, right? It goes to the cycle, and then it will come back to the origin back. So the idea is that, so that it will simplify your calculation, right? In terms of solving the efficiency, the work net output. So the idea is that, although the physical processes for real gas turbine is an open cycle, but for Brayton cycle, we convert that into a closed loop. Cycle. So there's an idealized cycle, which is a Brayton cycle. Right, so Brayton cycle, so instead here, so now we change the real gas turbine cycle into a closed cycle, which we call a Brayton cycle. So here again, And also, again, it's an standard air assumption where all the working fluid inside all these processes is air, right? So no mixture of air fuel, just air, standard air, so that it will again makes your calculation simplified, right? So this Brayton cycle is a closed cycle and it uses air as a standard assumption. And the combustion, the process that, the physical process gone through, we have changed that into a heat input, right? So heat input. So no need to consider the chemical process. We have to consider what is the product output, everything. So it just become like heat addition into the air, right? In work net output. And also, you have this an additional to complete the loop, right? So because you want to change the air that goes into the 4 and go back to its origin at 1. So you need to have this process, which is the heat rejection. Heat rejection, the Q out here. Okay, so that's the introduction. So what is the Brayton cycle all about? So it's a closed loop, idealized cycle with air as the working fluid, standard air assumption. And you have the additional of this heat rejection between 4 and 1. Okay, and we shall take a look at each this process. So from 1, 2, 3, and 4 for this an idealized Brayton cycle. So 1 to 2. So you have this air that goes inside the compressor, right? Goes to the compression. And in this Brayton cycle, we consider that as isentropic compression. As you know, it's isentropic means that the change of the entropy is positive or negative for isentropic compression. Positive or negative? Huh? It's 0, right? Isentropic compression is not positive or negative, but it's 0, right? It cannot, isentropic cannot be negative, right? You learned that in thermodynamics 1, right? Because it's irreversibility. I mean, it's losses. So how you can say friction is negative, right? Because friction is always is either 0 or positive. So that's from your thermodynamics 1. So isentropic compression means that the change of entropy between 1 and 2 is 0. So it means that there are no losses. The energy will not get lost, even though it mixes with the compressor, blade, everything. So we assume that there are no losses in the compressor. So in Brayton cycle, 1 to 2 is an isentropic compression. Okay, we shall take a look at the 2 and 3. So 2 and 3 is the heat addition, which is happen at constant pressure. Constant pressure. So it means that pressure does not change between 2 and 3. P2 equal to P3, constant pressure, heat addition, which reminds you of a diesel cycle, right? Diesel cycle, the heat addition happens at the constant pressure. And we shall take a look at 3 to 4. 3 to 4 is isentropic expansion. Again, I mean, we assume there are no losses in this turbine, right? So that's why isentropic is an isentropic process. Delta S equal to 0, change of entropy equal to 0. And then here you have the work net output. And 4 to 1. So it's the heat rejection. Heat rejection 4 to 1 is at constant pressure. So which is make our life easy. Once you see this constant, you know that P4 equal to P1, make your calculation easy, right? So you know that constant pressure, P2 equal to P3, P4 equal to P1. I mean, that's the simplification for your calculation in this Brayton cycle. Okay, so that is the basically the general all these characteristics of this Brayton cycle. So for gas turbine. Okay, so any questions so far on this cycle here? And also you will notice that, you know, there's a linkage here, right? So this is the main difference between a steam turbine and gas turbine. You have a linkage here, means that turbine, the work net output here is also used to rotate the compressor here. So it means that the work net output will be equal to the work of the turbine minus the work of the compressor. That's a gas turbine here. So yeah, I have a video. We can show you. I mean the mechanism of this gas turbine. How does this relation of this turbine compressor relate together? Okay, we'll have to include those in group B as well. So okay, so just check for group B. Can you hear the sound?
Yes, sir. Thank you.
All right, so yeah, we'll go and see this video just to show physically. I mean, how does this gas turbine looks like? You know, so yeah, you have to just identify what the process of the working fluid like goes into this gas turbine. So where does it goes about in compressor, goes to the combustion chamber, and then it goes the expanding in the turbine, right? And then the relationship between this compressor and the turbine.
Air. A lot of gaseous molecules floating all around us. It's great for breathing, and it turns out it's great for getting lights turned on. That's because air, along with abundant natural gas or other fuels, are the ingredients that combine in a gas turbine to spin the generator that produces electric current. If you follow the electricity you use at home or at work back through the power lines to your local power plant, you'll see that the process most likely starts with the work of the gas turbine, the very heart of the power plant. First, air is drawn in through one end of the turbine. In the compressor section of the turbine, all those air molecules are squeezed together, similar to a bicycle pump squeezing air into a tire. As the air is squeezed, it gets hotter and the pressure increases. Next, fuel is injected into the combustor where it mixes with the hot compressed air and is burned. This is chemical energy at work. Essentially, this is what happens in your family car's engine, but at about 2,900 times more horsepower. Actually, it's exactly like the turbine engines on jet airplanes. The hot gas created from the ignited mixture moves through the turbine blades, forcing them to spin at more than 3,000 RPMs. Chemical energy has now been converted into mechanical energy. The turbine then captures energy from the expanding gas, which causes the drive shaft, which is connected to the generator, to rotate. That generator has a large magnet surrounded by coils of copper wire. When that magnet gets rotating fast, it creates a powerful magnetic field that lines up electrons around the coils and causes them to move. The rotating mechanical energy has now been converted into electrical energy, because the movement of electrons through a wire is electricity. In what's called a combined cycle power plant, the gas turbine can be used in combination with a steam turbine to generate 50% more power. The hot exhaust generated from the gas turbine is used to create steam and a boiler, which then spins the steam turbine blades with their own drive shaft that turns the generator. What you end up with is the most efficient system for converting fuel into energy. And that's your GE Gas Turbine 101.
Okay, so that's a video. It shows that in the last section that the function of a gas turbine, it can use to power up your electrical powerhouse. I mean in the power plant, and also you can combine with a steam turbine. I mean in order to produce more power, right? And then the heat generated by your gas turbine can be used to reheat the steam plant. So yeah, mostly nowadays, I mean, this steam cycle and the gas turbine cycle has been used to power up the homes, everything. Okay, so I hope you got the picture, like how this gas turbine look like. I mean, I don't want to, yeah, you have that picture that steam cycle and the gas turbine is the same thing. So it's different, right? It's different, and you know that the compressor and the turbine are connected together in this gas turbine. Okay, so we'll continue back on our slide. Okay, so we'll introduce this process for the Brayton cycle. And now we're going to take a look at the parameters of this Brayton cycle, the work net output, the thermal efficiency, and all the formulas that is attached with this Brayton cycle. Okay, and so physically, this gas turbine is an open system, right? So it's physically, I mean, so we need to use the formula that is for an open system. And if you remember, that is in your chapter 4 of your thermodynamics 1. I mean, where you learn about the Q minus W equal to the change of the enthalpy, H. Right? So it's not the closed loop. Right? So okay, so this is for steady flow devices on open system. So you have this the first law of thermodynamics, Q in minus Q out, right, equal to the change of the enthalpy. So this is an open system, right? Instead of the closed system, Q in minus Q out, and plus the work in and output equal to the change of the internal energy, the U. You have the H, the enthalpy. So this is the main difference of the Brayton cycle and other cycle, the Otto cycle and diesel cycle, where you see the Q in minus Q out plus the network equal to the change of the internal energy, the U. But here for Brayton cycle is H, the enthalpy. Right, and we shall take a look at the diagram, the TS diagram and PV diagram. Let's we take a look at the PV diagram first. So here is from one that goes into the compressor. So it's an isentropic compression. So here is a PV diagram. So isentropic compression, S is constant. It's an isentropic compression. Delta S equals 0, 1 to 2, and 2 to 3 is the constant heat addition, constant pressure heat addition. So you have P2 equal to P3, straight line here, and it will expand in the turbine, right? So this is where the work output cycle. So the S is constant, delta S equal to 0, expand until 4, and then we go back into the origin 1 at 1. So it's a constant pressure heat rejection. So that's why you have a straight line, horizontal line over here. Right, and it's a TS diagram here. So 1 to 2, isentropic compression. So you have a vertical straight line going up, right? Delta S equal to 0, so no change in the entropy. So 2 to 3, heat addition. So entropy increase because of the heat addition. Pressure is constant here, goes up to 3. So at 3 would be the maximum temperature for the cycle, just like the Otto cycle and the diesel cycle. And 3 to 4 would be the expansion, isentropic expansion. And 4 to 1 will be the heat rejection, constant pressure, heat rejection. Okay. Okay, so any question on this cycle? All right, so now once you see this cycle, so I think this is quite familiar to you. I mean, right? So yeah, you can solve this based on your approach in your thermodynamics 1. Okay, so we shall take a look at the formula for the Brayton cycle efficiency. So here is a case where with a cold air standard assumption. So this is a new term here. Cold air standard assumption means that it's a constant specific heat. So constant specific heat means that we can use the equation that relates the enthalpy with the constant specific heat, Cp equal to the change of the temperature, right? If it's constant specific heat. So yeah, in tutorial, I've been exposed to you. I mean, what is the approach between the constant specific heat and the variation specific heat, right? So if constant specific heat, you can straight away define your enthalpy as the constant specific heat Cp and the delta T. But if it's a variation specific heat, then you cannot use this equation. So you have to go back to the air table. Air table is the table A17, the air, I mean the temperature, the table which shows the temperature variation. So once you know that temperature variation, you can find what's your H value, your reduced specific volume, VR and PR, everything. Right. So here we shall take a look first with cold air standard assumption or constant specific heat, where you can use define the H equal to constant specific heat and the delta T. So Qin equal to H3 minus H2. So this is based on the cycle. Right, so based on here, so Qin equal to H3 minus H2. Q out is the H1 minus H4, right? So that's why it comes about. Right, so here. And from that, you can expand that, right? So, because the efficiency is equal to the work net divided by the heat input, right? So the output divided by the input is the efficiency. And this, as you know, is the 1 minus Q out minus Q in. And so you put in all this definition over here, and you can have that in terms of the temperature. Right, and for the isotropic relationship T2 minus T1, P2 is equal to P2 over P1, right? It's from your equation from thermodynamics 1. So you can relate that T2 over T1 equal to T3 over T4. And so this is a new term here. It's called the pressure ratio for Brayton cycle. So it's equal to P2 over P1. Right, and you can relate that to put it back into the formula here. So you have the formula for the Brayton cycle 1 minus 1 over the pressure ratio power of K minus 1 over K. So this is the formula for if it's constant specific heat or cold air standard assumption, where for air is K equal to 1.4, right? And the RP here, which is the pressure ratio, is in terms of P2 over P1. Okay, so this efficiency for Brayton cycle. Right, so this shows the variation, right? What if we increase the pressure ratio? What would happen to the value of the efficiency for Brayton cycle? So typically, if you increase the pressure ratio, you can see that the thermal efficiency is increased over time, but you have a limit there. I mean, probably more than 25, you can see that it will goes to a limit. So you can't go like more than the 70%. So you have a limit there until like close to 65%. So, and typically, I mean, the pressure ratio is fall between here, 5 to 20. Yeah, because if you increase the pressure ratio, of course, the temperature will goes higher, right? So goes higher, the turbine blade um, will not withstand the high temperature range. So that's why typically we cannot go much more than this. Right, so yeah, like I said, the highest temperature is limited by this maximum temperature, even though you can increase the pressure ratio more and more. So it depends on the type of the gas turbine as well, the type of the blade that you use. Right, so now we're going to see for fixed value of the mean temperature and the max temperature, the network first increase with pressure ratio, what will happen to the thermal the efficiency. Right, so this is to see the pattern, right? So here with the case, if your pressure ratio is 2, so the work net output will be just, as you know, the work net output for this will be the area under the curve here. And but if you increase the pressure ratio up to 8.2, so we have a bigger work net here, and which is the maximum work output. But if you increase it more, sometimes the work net will decrease. Right, so it's not certain that if you increase the pressure ratio, your thermal efficiency will goes up. I mean, in some case from 2 to 0.8.2, it will increase, but after that it will decrease. So that's the pattern of this. If you want to increase the thermal efficiency of your Brayton cycle, increase the pressure ratio, we have to look. Sometimes you increase the pressure ratio, your thermal efficiency goes up. But after that certain limit, like for this case, 8.2, your pressure ratio will decrease. Right, so that's why you have a certain range of typical pressure ratio for gas turbine engines. So it's not that the more the pressure ratio, the more compressed that your gas in the gas